What?
All right. I lost the PI. Okay? Anyway, you feel comfortable typing the formula, the first one. Clearly, we don't have more than two significant figures. If you wanted more, that's what we do. Yeah. Although it's always better to go lower than higher in KC, in magnitude. So I'll probably put minus 0.126 when we test it. All right, for PI control, equals 1 over K times tau over D times tau divided by D times the parenthesis. And notice it's smaller in magnitude. PI controller will always have smaller Kc in magnitude than P.
Oh.
We didn't fit it with the threshold function. We'll see how it goes. Okay. All right. Tau I.
Can you go back to the Can you go back to the formula really quickly, please?
So again, this is the formula. So anyway you feel comfortable entering that. You can use your own parentheses, whatever. You don't have to do it my way. As long as you do it right, I'm happy. So tau I, a little bit to the right. So that is equal to D times, open parenthesis, 30 plus 3 times D divided by tau divided by parenthesis 9 plus 20 times D divided by tau.
You up? Yes, just once.
Okay, so our tuning is using Cohen-Kuhn method. That's right on the board what the tuning is. So
That's such a delay. I know.
for P control, KC is, and again, you want to go a little bit lower, so I'll make it minus 0.125. And for PI, KC is minus 0.109. And tau I is about 16, right? All right, 15.6. it's very sensitive to the delay. Small delay is bad, and I think I may have made the step change a bit earlier, and I may have underestimated a bit the delay. So this tuning is not going to be the greatest, but let's say it's in action. Anyway, that's what we got. Let's see. Might get a good score, but it will be a bit too aggressive. But it also gives a good opportunity to talk about what you look for after you put. No, actually, now we're going to run CSTR again. So, where is CSTR again? I think I accidentally. So drag CSTR again. DOSBox. We want automatic control and press immediately A to change the tuning because the default tuning is lousy. Oh, good. So, for proportional control, what do we do? For just proportional, we change the controller gain, and so I'm testing now the proportional control minus 0.125. Now, the software, as I showed you, sometimes hardware has the ability to have true proportional action. Sometimes it doesn't. The software doesn't have the ability. So how do I eliminate integral action? If I do just proportional control, I shouldn't have the integral.
0, 0.
But I can't do that. I have to put a tau I. So how do I eliminate the tau I, the 1 over tau I integral?
Very big.
Make tau I very big. So I will change the integral time constant to something really big.
1 million.
How about 1 million? Okay? Tau derivative is 0, so we leave it at 0. So to eliminate integral action, I put tau I, something ridiculously large. And notice tau d, the derivative time constant is indeed 0. So 4, let's see how I do. One thing is that it's aggressive, so you can see that the manipulator tends to move too much. That's not good for control valves.
Can you repeat again what you just did?
Okay. Oh. So, first screen, I choose automatic control. I started with the J, and your fingers should be ready to press immediately A to change the controller tuning. Every controller you can operate on automatic or on manual. Manual means you choose you, the manipulated thing. Okay? You enter the value for the manipulated input in manual. Automatic is the proportion controller, the PI controller, the PID controller, whatever control strategy you're using. So here we're going to test automatic with P control. So I'm going to press G and immediately A because I don't want to stay with a terrible tuning much more. So G and A, and I get this screen, automatic control tuning screen. So first I'm going to change KC. Notice this is 3 times larger than what we are getting now. It's minus 0.3. So press 1, enter, and I'll give the new value minus 0.125, which is what we got. Tau I don't want integral action if I'm doing proportional control. So I'll put a ridiculously large number. So I press 2 to get the tau I, and I use a huge number, I use 1 million. 10 million. And then derivative constant is 0. So I don't have to change number 3. And 4 is quit the screen and return to simulation. So we're ready now to return to simulation. So now we'll see how it does.
Wow. Mine is totally different from yours.
Yeah, because the beginning affects. But it should be still pretty close to the set point, at least at the beginning. But when disturbances happen, you may see that we don't return to the set point. So far, nothing significant has happened. It will not necessarily be the same. Here disturbance happened. Notice what happened. The disturbance came. Controller responded correctly. Temperature was dropping. It dropped the flow rate of the coolant. But notice we didn't return to the set point. That's the problem with proportional control. When we run the same thing now with PI control, we're going to say very nicely return to the set point. Here's now the set point change. Correctly, since I'm going to be down, increased. It's the luck of the draw how close we'll come. Actually, in this case, we're like it, we came fairly close. Some of you may not come so close. Yes.
Is that okay? Like mine is like going up and down, like it's an 8.0 earthquake going here.
You have a typo? You may have a typo. If it's getting really weird stuff, you may have a typo. Oh yeah, you have a typo. Press A. Let's see what tuning you have. Yeah, this is 10 times too big. It's minus 0.125, not minus. Yeah, here's off by a factor of 10 in the tuning. That's all. Here was a big disturbance. Again, you can see that we didn't return to the set point. And here is, if you remember that, that's where things got interesting. So what's going on here? It moved a little bit towards increasing the temperature, but look how far off it is.
Awful. What happened? I give it an F plus.
You can see now why integral action is needed. Okay?
What happened there? Like, what was the issue?
That I don't have integral action. If I don't have integral action, there's no guarantee that I'll go to my set point. We'll do the same thing with PI, with the tuning that we got for PI. Okay? But you can see, maybe we got a little bit closer, but it will never get there.
What does integral action do to make it closer?
Okay. We'll understand mathematically probably even today. So can we wait until after the break? Okay, let's do the PI now. That's good enough. We don't have to finish it. I mean, you saw the problem with PI. With speed control. Okay, let me escape that. Now let's run it with PI. So A, and I press J immediately A. And now I'm going to change controller gain to minus point. And careful, it's minus point, okay? And now it's supposed to be 109. And I'm going to change the integral time constant. Actually, do I need to change? 15.8, it's almost the same. Okay, 15.6. And that's it. Let's see how it does now when I have PI control. because, why do I have these big deviations? Because of the very bad initial tuning that was at the beginning. That really moved the system away. One thing you'll notice is that I have oscillations. You don't want to have oscillations, particularly if they're not dying out fast. This is not too bad, but it's not great. We'll take a full 15-minute break, but let's finish this. Okay? Here was a disturbance. Brings it back exactly to the set point. And let's see.
Who's not here? Who's skipping?
Joe is skipping. You say I was going to refer to him because we'll see if it beats Joe's score. Joe is the one who wants 60 again. There's a big set point change. We went immediately to the set point. A little bit of overshoot. This is another indication of aggressive control. Aggressive control means typically it's taken care by reducing the magnitude of Kc. So the fact that I had so much overshoot, I want to go here, I have considerable overshoot. This is an indication that my controller is tuned a bit too tightly. Here was a big disturbance. Return nicely to the nominal value. And in a minute we'll have the set point, the interesting stuff. Here was a big disturbance. Notice it returns exactly to the set point again. Integral action returns us exactly to the set point. Here's the big step change coming at the end of the screen. All right? So, immediately shuts off the flow rate of the coolant. Remember what peak control was doing? You couldn't get there. Because it's aggressive, you see quite a bit of oscillation. That's not desired. So my Kc is too high in magnitude. And that happened because my D was too low. I think I underestimated by 1. If I change D to 7 from 6, I think we would have a much better screen. So the fact that you see a lot of oscillation is not very desired. Still, we're going to get control graduate student, and we'll have a better score than Joe had. But our tuning is not so good. You have a lot of oscillation that is not going away fast. That's not desired. But still, you can see we're doing a fairly decent job now. Oscillations finally died out. So it took a while for the oscillations to die out. Somewhere here is where I blew up. Our score is going down below 130. It will be below 120 again. Almost done.
So with like an optimal controller, what average square error would you be looking for?
This is the head.
0.
Say again?
Like what would you look for the average square error if it was like optimal control?
Well, it probably wouldn't be much better than this. But because of the big step changes, it will never be 0. But okay, 150.
Oh, that's a beat.
Okay? Notice how rough it is with the tuning. Notice how rough our transfer function